Hey folks, today we're going to be covering our last lesson in our unit on kinetics and equilibrium. And today we'll be talking about changing equilibrium, on how we can take a system that is at equilibrium and cause it to shift either in a forward or reverse direction to achieve some type of desired outcome. So we'll see how we can affect reactions that are at equilibrium with today's lesson. Now we know from previous lessons that equilibrium systems are what we call dynamic. What this means is that they're in motion. They're changing. There's constant change forwards and backwards. It's not a static or something that is not in motion. Constant change forwards and backwards. It might look like it's at a standstill, but we have forward and reverse reactions occurring at the same time, at the same rate, so we have equilibrium. We still have collisions occurring, so this system is in motion. We know equilibrium has to be in a closed system, or it cannot remain in equilibrium. If we have parts of our reaction escaping, or matter from the outside or energy from the outside environment coming in, then the system cannot remain in equilibrium. But depending on the reaction, we might want to make more product or shift a reaction in one direction on purpose. And that's where today's lesson comes in. Now, shifting equilibrium has to do with a principle that I think makes you sound super smart. It's called Le Chatelier's principle. Now, Le Chatelier's principle says that if we take a system that's at equilibrium and we subject it to some type of stress, then the equilibrium is going to shift in the direction that's going to make the stress easier, or will shift in the direction of whichever reaction was made faster by the stress. And there's a lot of different ways to stress a reaction that's at equilibrium. But however you stress it, the reaction is going to try and compensate for that added stress. If you're trying to hold a barbell above your head, and we have plates here on either end, maybe this is 100 kilograms, and we add, let's say we just put one plate on the, left side, right side, however you want to look at this, and this is unequal, so maybe we have 100 kilograms, and now we have 50 kilograms on the left. Well, if you're stressing out your left arm here, your left arm is going to compensate for that added weight by applying a greater force just with the left arm to keep that barbell above your head. We don't need to put as much force on the right because we have a smaller weight there. But the added stress of 50 more kilograms on the left side means that our left arm is going to have to compensate for that and apply a greater force to try and maintain this barbell at equilibrium, which we can call just maybe like a flat plane here that's perpendicular with vertical. Now, a change in reaction rate in one direction, forwards or reverse, will cause a change in the concentration of both reactants and products until we get a new equilibrium established. Now, this is going to change the amounts of reactants and products. Remember, the amounts don't matter for equilibrium. What matters for equilibrium are the rates. Now, a forward shift will be a shift to the right, and a reverse shift will be a shift to the left. Forward shifts meaning the forward direction or forward reaction, reverse shift being in the reverse direction or in the reverse reaction. That's a little bit of background for where we're going today. Now, what are some of these stresses? What can cause these shifts at equilibrium? A couple different things. We can add or remove reactant. We can add or remove product. We can change the temperature by increasing or decreasing it, and we can change the pressure by increasing or decreasing the pressure. See if my pen's going to draw here. These have to do with concentration. So changing the concentration of reactants or products, changing temperature, changing pressure. Now we'll take a look at how each one affects a reaction at equilibrium, and then we'll do some examples with that. And what I'd like to do with this, well, I guess I'll go over this when we get there. We'll talk about each stress first. Adding reactant. By adding reactant, this is going to increase the number of collisions between reactant particles, and therefore makes the forward reaction go faster. Reactants will get used up as they form more products because the forward reaction is occurring faster. The products will increase and the reactants as they get used up will decrease. Removing reactant, this is going to be decreasing concentration. This will cause a decrease in the number of collisions between reacting particles, and it's going to make the reverse reaction occur faster. When the reverse reaction occurs faster, products get used up and decrease, and reactants will increase. Adding product is increasing the concentration of product. This will increase the number of collisions between product particles, and it'll make the reverse reaction go faster. As far as the change in concentration, this reverse shift will cause our products to decrease as they get used up and reactants to increase as we make more reactants. Removing product. This is going to decrease the concentration of products. It'll decrease the number of collisions between product particles, and it makes the forward reaction go faster. Since the forward reaction is occurring faster, reactants will get used up and their concentration will decrease, and the concentration of products will increase as more of them are made from the forward reaction. Increasing temperature is going to favor the endothermic reaction because endothermic reactions require an input of heat. And if we require an input of heat, if we have more heat around because of a higher temperature, then the endothermic reaction is going to be favored. It causes a shift of equilibrium away from the side with the heat to absorb the excess energy. Remember, we're going to write heat as a reactant or product in our reaction. And in an increasing temperature, we'll shift away from the side, from the reactant side. I guess depending how we're looking at the reaction, it could be on the product side, but we shift away from whichever side has the heat on it. And I'll explain more of that in the example. If the shift is toward products, products will increase and reactants will decrease. This is also going to depend on where the heat value is, if the reaction is endo or exothermic. If the shift is toward reactants, reactants increase and the products decrease. Decreasing temperature. This is going to favor the exothermic reaction, and it's going to cause the equilibrium to shift towards the side with the heat to release energy. Now, if the shift is toward products, products will increase, reactants will decrease. And if the shift is toward reactants, the reactants will increase and the products will decrease. This will depend on where the heat value is in the reaction, which we'll look at momentarily. Increasing pressure or changing pressure in general is only going to affect gases. And this will cause the system to bring the pressure back down to relieve the stress of an increased pressure. Once it brings the pressure back down, by shifting towards the side of the reaction that has fewer moles of gas on it. This is key. Fewer moles of gas. So if the shift towards fewer moles of gas is towards products, the products will increase and the reactants decrease. If the shift is toward reactants, the reactants increase and the products decrease. At this point, hopefully we're seeing that when we shift toward products, if we think of a reaction from reactants to products, a shift towards the products would be a shift to the right. Reactants get used up to form products, and products increase. So the shift in either direction is just going to change reactants and products and cause one of these to increase or decrease. So decreasing pressure, again, only involving gases. This will cause the system to bring the pressure back up by shifting towards the side with more moles of gas on it. More moles of gas means we have more particles of gas flying around. Therefore, we are likely to have more effective collisions, which would increase the pressure. Depending on which side we're shifting to based on concentration or based on moles of gas, if we're shifting towards the products will increase, the reactants will decrease. And if the shift is toward the reactants, then the reactants will increase and the products will decrease. Luckily, there's a few factors that cause no worries to systems that are at equilibrium. This includes catalysts, inhibitors, and surface area that have no effect on a system that's at equilibrium. This is because they allow the reaction to get to equilibrium faster, but once they're there, a catalyst and an inhibitor influence the forward and reverse reaction the same. So they're not going to favor the forward or reverse reaction. They'll affect both the same. Same thing with surface area. We're allowing for more collisions, and that means more collisions between reactants and products, and it'll affect both forward and reverse reactions equally, and therefore don't affect equilibrium. So we're going to consider the influence of the 10 different stresses we just talked about on this one particular reaction, which is the Haber process, the formation of ammonia, NH3, and heat. So we're just going to deal with this reaction. And what I want you to do, so we know that, we'll start here, this is exothermic. Right, so we think of our enthalpy and entropy. This would be favored because it's exothermic. And if we consider the entropy, feel free to pause this video and try this. We have a gas, and a gas. So if we look at the number of moles, we have 4 moles, we have 2 moles. Now, this is getting from 4 moles to 2 moles, this is getting more ordered. This is a decrease in entropy. If we think back to last lesson, we have a decrease in entropy and an increase in enthalpy. So therefore, having a negative delta H, that negative sign tells us that this reaction is spontaneous at low temperatures. So the heat value, we're going to treat the heat value in our reaction here, we're going to treat this like it's a regular product. Just like it's an NH3, we're going to treat the different stresses on that system just like heat is a product. And that should help here. We have the double arrow indicating that both forward and reverse reactions can occur simultaneously and that this reaction can achieve equilibrium. In all of these examples, I'd like you to use a seesaw with a fulcrum in the middle that represents the state of balance of equilibrium in this reaction. Now when the seesaw is completely level, our reaction is at equilibrium. We are in harmony. Now every time you stress this system, you can think of this almost like people. 1N2, 3H2 is going to balance with 2NH3 and some heat on the right hand side here, as long as we're at equilibrium. But if we start to add or remove different things, this seesaw can become slanted to one side or the other. And depending which way it's slanted, we always want to try and bring this back to our equilibrium level. We want to try and bring the seesaw back to balance. And we'll describe the change that we need in order to bring this back to balance and how it's going to affect our reactants and products, the amounts that we have or concentrations that we have of reactants and products. So for each of these examples, we'll be using the seesaw. Now consider the stress of adding N2. So we'll start with the seesaw here. We got the fulcrum. We'll try and draw this level all the way across. That's a completely level, flat line. If we add N2, now N2 is on the left-hand side of our reaction. If we add N2, we're going to add more N2 on this side. This is going to cause this seesaw to get slanted on the left-hand side. We're adding more stuff, more nitrogen gas, more people on the left side of the seesaw. Well, in order to balance this out, to bring our equation back to equilibrium, Le Chatelier's principle says that we're going to have to shift away from the stress, away from the added N2 over here that we're adding, and we're going to shift away from that to the right. We need more NH3 or more heat on the right side of this seesaw here in order to bring this back to balance. We shift to the right. Shifting to the right, which we call a forward shift, because if we add a reactant, it's going to cause a shift towards the product. It's going to cause a shift away from the added reactant. And the key here is that this is a forward shift. So forward shift simply means forward reaction. The forward reaction is going to occur faster, because we have more N2 over here, which means more collisions between N2 and H2, which means a greater and faster formation of ammonia. Now when we shift to the right, what happens? Well, we're going to use up N2 and we're going to use up H2 to form more NH3. So the concentration of nitrogen will decrease, the concentration of H2 will decrease, and will produce more ammonia. Let's remove N2. Again, think of the seesaw. If you have N2 over here on the seesaw and we want to remove this, if you take people off of the left side of the seesaw, well, if it was balanced, now you have less people there, it's going to be slanted. Now in order to bring this back to balance, this reaction, we have to get more N2 or H2 over here on the left side, which means we have to shift towards that side to make more. So this would be a reverse shift or a left shift, because when you remove reactant, we cause a shift towards reactants. We have to shift to the left in order to bring this seesaw back down. We got to put more stuff on that side, and that would be a reverse shift. During a reverse shift, nitrogen will increase and hydrogen will increase as we decompose ammonia to make more N2 and more H2. So then NH3 is going to decrease. So we're shifting left. Reverse reaction occurs faster. And the reverse reaction is decomposition of ammonia to form nitrogen and hydrogen. Adding H2. So if we add H2 here, our seesaw is going to get weighed down towards the left side because we're adding more H2. We're increasing the concentration. This will cause a shift to the right to try and bring that right side of the seesaw down, which means we need to increase the concentration of this. The only way to increase the concentration of ammonia is to have more effective collisions between nitrogen and hydrogen to form more ammonia. When that happens, we use up nitrogen and hydrogen, so their concentrations will decrease, and we can therefore increase the concentration of ammonia. Remember, this is simply a process to produce ammonia. This reaction occurs in industry, very common, and it would kind of make more sense that if you want to make more ammonia, well, add more of what it takes to produce ammonia. Put more nitrogen and hydrogen in there, and we'll produce more ammonia. That should hopefully make sense. When we remove H2, it's like removing people from the other side, from the left side. It's going to make the left side of the seesaw higher because we took stuff off of that side. It wasn't balanced. We removed hydrogen. Our seesaw is now high on the left-hand side. So this will cause a shift. Reaction will want to move towards the left to bring that seesaw down. This is a reverse shift. Removing reactant causes a shift towards reactants. Shifting left will use up NH3 and cause this to decrease. And in order to bring our seesaw back up, we need both of these concentrations to increase. Adding NH3. And I'm going to look at the product side. Adding NH3 will cause our seesaw to get heavy on the right-hand side. If we're heavy on the right, we need to shift away from that towards the left. So this is a reverse or left shift. Adding a product causes a shift away from the stress towards reactants. Left shift will use up NH3 and cause this to decrease and cause the concentrations of nitrogen and hydrogen to increase. So these shifts are telling us which reaction is occurring faster, the forward or reverse reaction. We're always shifting towards the side that needs to be brought back down to level. Bring that seesaw back to level. Now removing NH3 will cause our seesaw to be light on the right-hand side, which will cause a shift towards the right in order to bring that seesaw back down. So removing a product makes us light on the right-hand side of the seesaw, which will cause a shift towards that lost product in order to try and produce more product. Anytime we shift right or in the forward direction, we use up our reactants N2 and H2, so their concentrations will decrease and will increase the concentration of our product. So NH3 will increase its concentration. Changing temperature. We're going to treat this using the heat value in a reaction just like it's a regular reactant or product. So if we increase temperature, our seesaw gets heavy on the right-hand side. We're adding more heat, we're adding more people on the right-hand side of our equilibrium equation. This is going to cause a shift away from the heat to the left, or a reverse shift, because increasing temperature causes a shift away from the heat. So we treat that just like we would a changing concentration of reactant or product. And again, reverse shift will use up the ammonia and decompose it into N2 and H2, increasing both of their concentrations. For the opposite, a decrease in temperature, this will cause our seesaw to get lighter or higher up on the product side. This will require a shift to the right or a forward shift in order to bring that seesaw back down, which will decrease or cause, because decreasing the temperature causes a shift towards the heat. A reverse shift will use up our reactants, nitrogen and hydrogen, causing them to decrease in concentration and increase the concentration of ammonia. Pressure. Remember, pressure has to do with the number of moles of gas on each side. So an increase in pressure here, well, we have 4 moles here and we have 2 moles here. So if we increase the pressure on this reaction, we're going to have a shift towards the right because we're going to try and produce fewer collisions because of that increase in pressure. So we're going to shift to the side with fewer moles of gas. In this case, it'll be to the right, so it's a forward shift. A forward shift will cause H2 and N2 to decrease, and the amount of NH3 to increase. Now the same holds true for a decrease in pressure. Again, we have 4 moles on the left, 2 moles on the right. A decrease in pressure will cause a shift to the side that will increase the number of collisions towards the side with more moles of gas. More moles of gas mean more collisions, so it's a shift to the left, which will cause NH3 to decrease and N2 and H2 to increase. Now, a funny way to kind of look at Le Chatelier's principle, I think this is pretty spot on. Don't worry about me. I know it like the back of my hand. Consider the equilibrium reaction. A plus B yields C and D, and assume they are either gas or aqueous. Now pretend you're a truck driver and the reactants and products are two sides of the road. The principle states that if there's more crap on one side, you shift towards the other. Simple as that. I kind of think of it as a truck driving down the road. And as you veer off to this side, you kind of shift to this side, kind of like somebody just kind of banging back and forth on the guardrails on the expressway. And all the whole while trying to get to this equilibrium position straight down the road. We'll do a couple examples here with everyone. This is a pretty tough topic and a tough concept. So make sure you're writing down any questions that you have. Make sure you come and get them answered. We'll do each of these here. Feel free to pause the video, try the question, and check your answer. So given the equation for a reaction at equilibrium, explain in terms of Le Chatelier's principle why the concentration of SO2 increases when the temperature is increased. So when we increase the temperature, what we do with that, we look at the energy value, the heat value, and we treat this just like it was a product. Now we're looking for why this is going to increase. Why is SO2 going to increase? Well, if we increase the temperature, we increase the heat content of the system, and therefore this reaction gets weighed down on the right-hand side due to the increased energy here, which is caused from the increase in temperature. So the stress is an increase in energy in the system, which makes our seesaw lower on the right, which means we're going to want a shift to the left away from that. So Le Chatelier's principle states that an increase in temperature favors the reverse reaction, therefore increasing the SO2 gas concentration. So we shift away from that added energy, which is a left shift, which will increase the concentration of SO2. Le Chatelier's principle says that we shift away from the added stress. Next one, a student makes an aqueous solution of lactic acid. A formula for one form of lactic acid is shown below. The solution is placed in a sealed flask to be used in a laboratory investigation. The equation below represents the lactic acid equilibrium system in the flask. So we get our double arrow here indicating equilibrium. Each of these are in aqueous form. Explain in terms of the reaction rates why the concentrations of the reactants and products remains constant in this system. When you have to explain in terms of something, make sure you mention that in your answer. So the reaction rates, well, equilibrium means, we know we're at equilibrium here. Equilibrium means that the rates of the forward and reverse reaction are the same. So reaction rates for the forward and reverse reaction are equal. Therefore, concentrations won't change. Next question asks to explain in terms of Le Chatelier's principle why increasing the concentration of H plus increases the concentration of lactic acid. Well, if we think of this fulcrum as where our yield arrow is, if we increase the concentration of H plus, our seesaw gets weighed down on the right hand side, which would cause a shift to the left, which will increase the concentration of lactic acid. So in terms, I'm going to put this up here. So Le Chatelier's principle states that an increase in product causes a shift towards reactants or away from the stress of added H plus, which increases the concentration of lactic acid. So you want to be careful how we word those when we're explaining in terms of Le Chatelier's principle or in terms of reaction rates. Now these are questions that came from recent past Regents exams, and you can see with each of these that you have to explain in terms of Le Chatelier's principle. And chances are you'll see something similar on your exam this year. Hopefully you're not confused. All we got to do is see which way a system would have to shift in order to relieve a stress brought onto it at equilibrium. And those stresses can come in the form of a change in concentration, pressure, and temperature. If you have questions, make sure you write them down and make sure you come see me in order to get them answered. Have a great day, everyone.